multiplications are done and defined with respect to a scalar field. And this field is not our electromagnetic field, so it's good to learn about some of these languages of mathematics. Field means something else to them, not our field, not our E field, not our H field, not our potential. Okay? And so this is true, and you also have this other thing, U plus V is equal to V plus U. This is called commutative under addition. If you add two things, it doesn't depend on the order, and then you also have this kind of thing. And then if you have them multiplied by a field, a scalar number, this is also true. You can multiply the scalar number first, and then multiply by the vector u later on. This is true. And then you have this distribution when multiplied by the sum of the two fields. This is true. Okay.
So
Yes?
here U is a vector, alpha, beta are scalars.
Yeah, alpha and beta are scalars. V is a vector. V and U are vectors. Okay, I use Roman alphabets to denote vectors, Greek alphabets to denote scalars. And then you can have this kind of thing too. Alpha U plus V is equal to alpha U plus alpha V. And then usually there is an identity element under addition. And in this case it's 0. 0 plus V is equal to V. Okay? Under addition. So you can say all vectors satisfy these properties. But all matrices also satisfy this property, right? The thing of U and V has been matrices. All matrices satisfy this property. But what is an additional property that a matrix can have that a vector cannot have? The inverse, that's right. If U and V had been a matrix, then they could be a matrix multiplied by this. This is called the multiplicative inverse for matrices. Vectors don't have this property. I mean, this property is absent from vectors. Vectors cannot have a multiplicative inverse.
Professor, how come you don't have the multiplicative identity for the vectors? I think you should also have it.
You can have, it's just one, right? It's just one.
Yeah, it has to be correct.
Just one, okay? And then there are a lot of interesting concepts in mathematics that maybe I don't know a great deal about, but I just hear about them. Things like rings. Rings are objects that are closed under addition and multiplication. Integers form a ring because if you multiply two integers, you get integers. If you add two integers, you get integers. Okay. So they're closed under addition and multiplication. Maybe I can denote multiplication. Another example of a ring is polynomials. If you add two polynomials, you get polynomials. If you multiply two polynomials, you get polynomials. But rings don't have their inverse. Integers don't have the inverse. What is the inverse of 365? It's not an integer anymore. Okay, what is the inverse of a polynomial? There's no inverse, right? So rings are entities they're closed under addition and multiplication. Okay? So those are rings. You can think of FFT as a multiplication by polynomials. What are you doing when you do an FFT? You do like n is equal to 0 to n e to the in times the number times an, right? And this is the FFT of A or something, and this can be thought of as x to the n, right? So FFT is this kind of polynomial interpolation. So you can think of the study of polynomial rings the same as the study of polynomials. There is a very famous theorem that some signal processors study called the Chinese remainders theorem. Do you know what that is? It turns out that if you divide an integer by another integer, you don't get an integer, you can get an integer plus a remainder. Right? You can divide a polynomial by a lesser polynomial, you get a polynomial plus a remainder. Okay? So rings have this kind of property. So it turns out that you can have a very complicated polynomial or very complicated integer. You divide by two numbers, you have two remainders. Or maybe you divide by three numbers, you have three remainders. And from the remainders, you can determine what the actual number is. That's called the Chinese remainders theorem. Have you all heard of this? What about the Chinese people in the audience? Have you heard of this? You never heard of this, right?
I think they teach us in middle school.
What?
They teach us this in middle school.
Middle school, Chinese remainders theorem?
We just call it remainders theorem.
Oh, okay. Okay. So there is this this general by the name of Han Xing. And he has a way of counting soldiers called Han Xing Dian Bing. It means that he counts soldiers using Chinese remainders theorem. He had the soldiers lined up in different formations. And then he just counts the remainders. And then he can tell how many soldiers there are in his platoon or in his army. You know, so this is let me see if I can write this well. Right, this is Han Xing. Okay.
You talking now? I just will go over there. Oh, okay. Oh, what's up? Yeah, so I have
Way of teaming, right? So he knew how to count soldiers using this Chinese remainders theorem based on this integer ring. Maybe he's Korean because his first name is similar to so Chris might know him.
Yeah, just last week.
So-
Seconds or whatever it is.
So integer ring is something like that, and then you can learn about this. And there are a lot of other things like groups. Groups are things that are close under addition. Oh, just one mathematical operation. If you add two things and it still belongs to the group, we call this the group of things. Sometimes that operation, the binary operation, can be multiplication. Like matrices form a group in the sense that when you multiply two matrices, you get the matrix. So those forms groups. Okay. So these are the kind of things that you can learn from the mathematicians. Maybe you can just learn about them so that when you talk to them, you sound intelligent. You understand what you mean. Otherwise, when you talk about rings, fields, you know, vector spaces, and you will learn about things like Hilbert spaces, Banach spaces, Sobolev spaces, Lyapunov spaces, and all kinds of things, right? They all sound very Russian, but those are the mathematical spaces that we should learn about. And we'll talk more about this in the next lecture. Okay.